So then, without further ado, good afternoon. Thank you for joining us on our third Lunch and Learn webinar series. So this is our TA Smart. Well, we're covering our TA Smart today. Excuse me, I'm just letting someone back in. So just to go over what we're going to be covering, we're going to be touching on the TA Smart's fundamentals and control principles. We're also going to be talking about the key elements of the TA Smart, so the features, how it's made up, what it consists of, what comes out of the box effectively. The flow measurement, accuracy and the control. We're going to be talking about applications, so how we intend to use these from a commercial aspect, where their placement would be from a system point of view, from a project point of view. And also talk about the connectivity options that are available within the unit itself. And then finally, we'll just touch on the HyTune application for the TA Smart, which is where we do all our configuration and commissioning. So what is a TA Smart or a smart valve hydronically? Well, it's just a control valve. That's all it is effectively, but it's controlled in a different way than a usual standard typical control valve. So if we take a look at the essential building blocks of how the TA Smart or a smart valve is put together, typically we have a control box, which is our smart box that sits on the back of the valve. The valve body itself, obviously to house all of the components. Our C part, which is our plug and seat mechanism. This is what is actually controlling on the valve, and the actuator above it, which is driving that control. Then our temperature sensor, which is mounted internally and connected to the smart box, and our second temperature sensor and the housing, which is mounted on the opposite side of the valve and is also fed back to the smart box. And these internally come back to the control system, so they are fed and output back to the BMS effectively. So why the need for a smart valve? What is the drive for the whole valve itself? What's the necessity for it? So if we take a look at a typical feedback loop with a standard control valve, just a standard linear 2-port control valve, not smart or anything in any way. We start with a room which requires a certain temperature. So this temperature is measured by a temperature sensor, and the value is X. And this is our control value. It's sensed by the sensor, which can be affected by a number of things, such as how many people are in the room, or if the sun's shining through the window at a certain time at peak times, and these disturb, etc. So these disturbances to the room temperature affect the temperature control. So the sensor sees, excuse me one second. So the sensor sees the current temperature, which is our X value, and that's taken as an input by our controller. The controller takes the set point value, which is U, which we can see here, and calculates the deviation between the set point U and the measured temperature value X. Based on this deviation, the controller will apply a certain gain, which is shown as our K2 in the controller. And this is used to calculate a position signal, which we can see here, out of the controller. The position signal, which is communicated to the actuator, will position itself according to which will position itself according to the voltage supplied. So 0 volts would be closed typically. The design position would be 10 volts, and 50%, 5 volts would be open. Sorry, 50% of the valve open at 5 volts on a standard linear 2-port control valve. When the actuator is at the correct position, The valve will be at a different lift, which will also be a different kV from when it was further open or further closed. And depending on the available on that kV value and the available differential pressure at the valve at that point in time, a certain flow rate will be flowing through the valve. And according to the flow that is now flowing through the terminal unit, we will get a thermal output coming out of the terminal unit, which will hopefully compensate for the deviation in the room and satisfy our room temperatures. Now, this is not quite true. So the whole process can take 10 to 40 minutes depending on the building and the type of control and the different delays that are playing a role in this type of control. So the general principle is that we send a position signal to reach a lift. That's what we do out of the controller, and then from this lift we hope we'll get a flow. But will we get the flow that we believe we would get according to the different curves and properties of the components? Well, probably not, because there are certain challenges. There is the hydronic network, where there are delta P variations and other things impacting the possibility to obtain a certain flow. We hope that flow will give us a thermal output, and that will help us to compensate for the deviation in the room. But there is another difficulty. Even if I provide a terminal unit with a generous flow, I still might not get any thermal output out of it. So imagine there is a lot of dirt that's clogged into the terminal unit and that's accumulated on the heat exchanger. This will diminish the ability of the terminal unit to deliver a thermal output. So therefore, you might be at the right flow and still not get a good power out of the terminal unit. So we are faced with these two difficulties. The first, our hydronic difficulty, which is expressed with a common formula, where the flow Q is equal to the kV times the square root of the dP. With the delta P variation that can happen, the flow that we're obtaining at the terminal unit is not something that is completely under our control. And the second difficulty is the thermal difficulty, where the power output depends on the flow traversing through the terminal unit and the delta T experienced by the fluid when it's going through that terminal unit. So these two difficulties are now non-linearly related to each other, making this problem a little more difficult now. So in a usual hydronic system, to get around these problems, we can allow the feedback control loop to perform several loops of feedback, and little by little it recalculates and recompensates for the new deviation within the room. So eventually we get what we want in terms of room temperature. But this obviously can take a long time to achieve. And equally, it can't be rushed, as we could introduce instability to the system. So we have to be careful on that front as well. So if we look at the different characteristics for a typical system, we have a terminal unit characteristic, which is non-linear. So unlike the actuator that's shown here, which is a linear characteristic, the terminal unit characteristic is non-linear due to the physics of its exchange. Then we have a control valve with an equal percentage control with a nice kV characteristic according to an inverse shape of the terminal unit characteristic. If we compensate this non-linearity by this one, and we then select an actuator that works essentially in a linear way, the difficulty we have is the dP variations. So the hydronic network is introducing dP variations into the system, which make the flow curve that we would like to get to manipulate the terminal unit not look different to the mechanics of the one that we've chosen. So if we have a system that works against us, and when combining this with a control valve that is good enough, So we give a control valve with an authority of 0.25, which is the minimum authority we should always meet on 2-port control valves. We get a global circuit characteristic of the power output of the unit, which is shown in P, in function of the control signal, which is U, coming out of the controller, which is nonlinear and which would not be easy to control at these initial steps of demand. So you can see the linear dotted perfect line, and this is realistically where our global characteristic is coming from. So to compensate for the hydronic difficulty, we took a newer approach at first than simply working with standard control valves. So we introduced differential pressure control into the control valve to make a pressure independent control valve with a self-acting DP controller, which is now acting by itself to facilitate the life of the control valve. And the control valve continues to do its work on its KV characteristic. But now the DP controller internally of the valve is absorbing these changes of pressure that are induced by the hydronic network and have flattened this curve to make the valve's life as easy as possible and give us this global characteristic that we can now see at the end. So we are now much closer or tighter to that straight linearity line as possible, and we should achieve a nice and stable room temperature. However, with PICV, this doesn't solve the thermal difficulty that we spoke about previously. So if your terminal unit is oversized or damaged in any way or suffering from dirt, we won't get the power output that we expect. So if we look at the smart valve and what it does in this type of control, it's the same as before, but with one exception. If we consider the black box that's shown on screen as the smart valve, there is a sub-control loop that's taking place locally. Now, this sub-control loop is measuring the flow and feeding it back to the actuator with a new target, so that the actuator will try to reach the flow as received by the controller, and this is what is changing, because now the input received from the controller is no longer a position signal, it's a flow signal. So when we get 10 volts, we should get to the maximum flow for this terminal unit, and when we get 5 volts, we should get to half of the flow. So the smart valve with a sub-control loop, which will in a relatively fast way, which is within a few seconds to a few tenths of a second, will adjust the flow as you want to get it. So the flow is reached, but the hydronic difficulty is not really solved. The smart valve is just a standard control valve with a unique plug and seat. It's not like a pressure independent control valve where we are buffering differential pressure or changes in differential pressure. So the smart valve must compensate for everything. So if there are any thermal and delta P variations in the system, the valve has to compensate for these factors, meaning the valve will constantly have to operate and adjust its position to get to the target that's been assigned by the controller. Then we still have the thermal difficulty. Once we get the flow, are we sure we're going to get to the power output? Well, that depends on a few circumstances. So we're going to have a look at that in just a moment. But first, let's have a look at how it operates in terms of control. We can see we still have our terminal unit with its non-linearity, so we can see that the physics are exactly the same. But this time we have a valve that, according to a certain signal, will position itself to the lift. So these two are related linearly, and it will give you a flow according to a curve that we choose to be equal percentage, so that it compensates for the curve of the terminal unit. So this time we can see we've simplified the process. There's no longer the actuator curve that's playing a part into it, or the hydronic instabilities or very DP variations that are playing into this, because we've condensed that with the control valve, with what it's doing by monitoring the flow across itself. Because of what's happening in the black box of the smart valve. So we now are getting this final curve, which when combined to the terminal unit, gives us this global circuit characteristic that is quite good. So the hydronic difficulty is still there, and the smart valve must constantly compensate on the unique control mechanism it has, and that affects its controllability. Now we can look at the power control mode with a smart valve. So the story is similar as before, except this time we take the power as the black box in the smart valve. So now we have a sub loop of control, which takes the power output measurement and then drives the actuator to bring the valve at this power through the terminal unit. This is because the input signal coming from the controller is now being interpreted as a power signal. So we now send as a signal a value to be reached in terms of power, and the power output will be reached. This power output will then be able to compensate for the deviation. So we still have a thermal and hydronic difficulty, and the valve needs to deal with them as much as it can. So now if we look at a graph of what it does, we get an almost perfect picture. So we get the power P that is linear with the control signal out of the controller U. So this is the dream of control theorists. A perfect line is what you need if you want very good control or a very good control system. But this is hiding a lot of what's happening inside the black box with the sub-control loop inside the smart valve. So the net result looks perfect. We get to the power we want to reach to compensate for a certain deviation faster, which is an advantage in terms of control to be reached quickly where we want to be in terms of reaction. And the hydronic difficulties are still present, but the valve can work with this. So if we take a look at the key elements of the TA Smart. So we have our smart valve and the smart box. This is where all of the brain control work is being done. So this runs our flow measurement and reads our temperature sensors. It instructs the actuator on where to position the control valve itself, and all of our communication, all of our input signals, our power supply, Modbus, botnet, or connectivity that comes into the valve is also wired and works wirelessly through the smart box itself. We then have the spool chamber, which is our ultrasonic flow measurement section. So this is where our flow is being measured. So typically we use time of flight principle. So we're measuring the flow with the pressure and against the pressure, because obviously with pressure the flow would be faster and against it would be slower. So we take an average of these two together and it gives us a very high accurate flow measurement. We then have the C part, which is our high rangeability, so we can control down to very low flows. Equal percentage plug and seat mechanism, so this is what's giving us that characteristic curve that we saw on screen earlier. And then on top of that is mounted our TA Slider 500 smart valve actuator, or SV actuator, which dynamically positions the valve to maintain our input flow or power. It's worth noting the actuator is unlike our previous sliders that we use on our TA modulators and compact Ps, where we use the TA dongle to talk to the actuator. We don't have a dongle with regards to the smart valve. The smart valve is communicated to wirelessly via Bluetooth or through networks, as I'll show you later. But all of the commissioning and setup is done through the app itself and wirelessly through Bluetooth into the smart box. We also have our internal temperature sensor. So this is what's measuring our temperature of the media inside the valve. And then we have our remote temperature sensor, which is placed on the opposite side of the TA Smart. And this is what's giving us our delta T and also is what's helping to calculate our power. And then with the smaller ones, with our 20 to 50 mil DNs, we actually get a temperature housing in the box. So this is a housing for the temperature sensor to be sat on the opposite side of the position of the valve. So if it's on the flow, if the smart's on the flow, the housing goes on the return, or vice versa. And we can tell the valve through the app which side it's actually sitting on. So if we then look at our TA Smart construction for the DN65 to now up to 125, again, exactly the same things. We have the smart box, which is positioned on the back. So again, this is running all of our flow and temperature sensors and what's telling the actuator to move the control plug up and down. And then our spool chamber. So again, our ultrasonic flow measurement device is in this bottom section. So that's constantly monitoring and measuring flow and recording that within the smart box. And then our C part, which is seated just underneath the actuator itself. So again, our high rangeability, low flow positions, equal percentage plug and seat mechanism. So this is what's actually controlling inside the valve itself. And then our slider 750 SV actuator. So exactly the same. We don't connect to the actuator itself. We just talk to the smart box through the application itself, or through our laptop if you're connected to the network, which I'll show you shortly. And then our internal temperature sensor. We also have a secondary remote temperature sensor, which isn't shown on this image, unfortunately. But again, like the previous one, we have a secondary line that comes out next to it with the same amount of cable, and this is to be mounted on the opposite side. The only difference with the flanged version is we don't actually supply a housing. So that has to be built into something else. So maybe a test point, and you screw the housing, you screw the temperature sensor into that, or a PT 1000 pocket. So just to touch on the variability of control modes in brief, we have seen all of these anyway. So our flow control, which is either over bus, so Modbus or BACnet, or via 0 to 10 or 0 to 20 milliamp. So this is our signal into the valve to be able to provide a target as a percentage of our assigned Qmax. So that's our maximum flow. Power control, which again over bus or our analog signals, and this provides us percentage of the assigned Pmax, so the max power. And position control, this is something that we probably wouldn't typically see in a commercial aspect or on projects. This gives us a percentage of the assigned maximum stroke available for the valve. This is something that's typically used in-house for testing and things like that, but there is a position control available if need be. Over the top of those, and these can't be placed as a separate item, so we can't control just via DT limitation. We have to overlay this as a secondary control to either flow or power position. And this will control and limit our delta T based on either flow control being the main function or power control being the main control function. And we can also do temperature return limitation as well. So we can return those, we can restrict those, limit those return temperatures coming back onto the system. And this is all configurable with the HyTune mobile app, and we can also do it through a local area network and be connected directly into your laptop or via the cloud, so we can physically make changes that way as well. And then we have our TA Smart Valves key features. So the versatility of our control mode. So again, as I say, we can do flow, power and valve position control, plus the DT limitation and the return temperature limitation. We're highly accurate on flow measurement, which I will go into shortly, just to show you some facts and figures on where we are with regards to how accurate we record flow and how accurately we record power. Wireless commissioning, so as I say, everything is done through the smart valve or through a local area network connection. But with the smart valve, there's no cables, there's no adapters, everything is done through the app itself. So a high controllability and rangeability. So it's best in class for flow control and rangeability. So that means we can control down very low, and I'll show you why that's important shortly. Fast response time. So obviously, as we saw over the sub-control loops, we are now able to do those changes and make those system changes very quickly over that sub-control loop, because we are constantly monitoring the flow, the temperature, the power output, and we get ultimately a fast response time. We also have great installation flexibility and reduced size and weight. The valve itself is very small, it's very neat compared to some of our competitors. We actually end up with the smaller valve, obviously the housing unit and the valve itself. So other manufacturers do a similar product, but these might be in 10 pieces that you have to put together, and you also need to then obviously make joints either side of those various pieces. So it can be quite difficult. And the unit, as stated, is IP54. So we're covered from splashing and dust proofing. So versatility in communication. So this is just to show off really and reiterate the types of communication that we have within the unit itself. On the left hand side is our HyTune, is a screenshot from our HyTune app itself. So this is the screen you will see when you're connected and in interfacing with the valves themselves. This is all done over Bluetooth 5.0, so on Android or iOS. So no cables, no laptops or dongles needed. Bus communication, so we can do Modbus and BACnet. We can do Modbus RTU and MSTP, and we can also do Modbus TCP and BACnet IP. So there are 4 that we can select from effectively, depending on how you wire it and how it's being controlled. And again, our 0 to 10 VDC or 0 to 20 milliamp or 4 to 20 milliamp is our input from our BMS PLC, so we can control the valve that way. And we can also get feedback back to the BMS, which is just 0 to 10 volts VDC. We don't do 0 to 20 or 4 to 20 milliamp on output. We have the web app, which is with our HyTune on LAN. So we can connect our laptop to the network, and as long as they're on the same network, we can search for the identifiers and physically pick those up and start making configuration changes to the valves on a larger screen. And we also have the MQTT, which is to and from the cloud. So we can talk if the valve is wired to a network over the internet. We actually can talk to the cloud, and from it, then we can set projects up and set the valves up so we can physically see what the valve's doing. We can also extract the data from there, and I'll talk about that in just a moment. And this can all be facilitated to the engineer who's delivering it on site, and then subsequently he can give people access to other engineers to be able to view it. It can be given to a customer, and they can give access to certain people within the business that need to see or retrieve data. And then lastly, there's the wireless communication. So this is a wireless communication that talks from one smart valve to another. At the moment, this is in development. So everything is there ready for it to go, but the wireless system, the thread network itself, is still in development. But it's just to show you that there's future proofing and more available as the product grows. So flow measurement, as I said, we use an ultrasonic flow measurement device, and This gives us a high accuracy of flow. We can also use for all regimes at any temperature, so we're not just restricted to an accuracy at certain specific temperatures like some others are. And we can also cover glycol mixtures up to 57%. So as you can see from this table here, we're actually at 3% at the majority of the flow range, and it just tails off towards the end and goes to a 5% accuracy, which is not bad at all. And from an installation point of view, for the DN20, although they still say 32 and 80 on the larger ones, so for the DN20 to 50, we are 0 diameters required before the valve, and for the 65 up to 125, we require 5 diameters on those larger size valves. The valve uses 2 PT1000 sensors, as I mentioned previously, and these are class AA. They're calibrated together as a pair and provide improved accuracy at low delta T's. And as you can see from the smart valve itself, from a plus or minus view of a Kelvin, we're within 1% realistically of an accuracy. And leveraging accurate flow and temperature measurement, the TA Smart also provides accurate power measurement in both heating and cooling applications. So we can see our flow accuracy is at 3%, and our delta T accuracy is roughly between 1.2 and 0.8%. So on average, say about 1%. And then our power accuracy is within 4%. So this is highly accurate from all point of view. So the smart valve is able to control flow down to 0.5% of its nominal flow. So the amount of flow that's permitted through that valve. So this means we can come down to a very small amount and gives us a highly accurate control throughout the heating and cooling season. What you can see from these graphs is typically for 80% of the heating season, we're actually only going to be delivering 50% of the design load, which only represents 20% of the flow. So we still have this full range of flow available for the last 20% of the year. So where we're getting up to the high 80% and 90%, typically we're only talking days here throughout the year itself. So it's a very small amount. Whereas, as we say, at 50% load, we're covering 80% of that heating season. So as you can see, this is a very steep curve. So it's vitally important that we have a control valve that is able to, one, go down to these low flows and is also able to control well at these low flows. So the equal percentage characteristic that we give to the valve, when you look at it from a graph point of view, you can see that this last 20% is typically half of the availability of the valve, or just below half of the availability of the valve. It's non-linear, so it's not 50%. So at 20%, we still have 5 volts of controllable flow signal to be able to deliver flow or power. And this last item, most of this we've already touched on, but it's to touch on the logging time frame options. So the cloud itself, which will be the basis of our next Lunch and Learn series, we will be talking about, excuse me one second. We'll be talking about how the cloud works, how you set it up, and how you assign a new valve to the cloud itself, and then ultimately how you can retrieve the data. But I've included this just so we can see the logging time frame options. So as you can see, we will, on an extra long login, this is keeping 13 months of data. So every hour of the day, it's logging for a whole 13-month period, and that is fully retrievable from the cloud itself. or the long login, which is doing 31 days every 1 minute. Our fast login, 7 days every 15 seconds, and then our extra fast, which is over a 12-hour period, is every 5 seconds. So, and you can stipulate this within the cloud of how much data you want and how much logging you would like to see. So, applications. Typically, we wanted to show some applications of where these valves are going to be installed and how they're intended to be used. So from a heat pump point of view, the TA Smart can be used on the primary side of the ground source heat pumps to control the power output from the geothermal loop. So we can see both of those here. And we can also monitor the power output on the secondary side of the heat pump itself. So obviously with the temperature probe on the return and our internal on the flow, plus our flow position, we can stipulate how much power output we want from that secondary side, or certainly monitor. On a 4-pipe system, so variable flow, the Smart can be used to control the flow on our injection loops, and it will also provide monitoring of the power which is being consumed by each unit, and that data, as I say, is available within the cloud, and you can extract that to see or to offer up to your client if need be. 4-pipe systems with zone measuring, so we can use to provide flat power and flow monitoring of each zone where they are placed typically on here. So we've still got standard PICVs on the AHUs and fan coils, but on each zone, instead of having commissioning sets or anything like that, or a heat meter, we basically use the TA Smart instead of isolation heat meters and flow measurement devices, and we can provide all of the flow monitoring and power monitoring and also isolation of the zone itself. For heating and cooling systems on variable flow, again, we can be used to control the flow or power on the ejection loop itself. It'll also provide the monitoring of the power being consumed by each circuit AHU. And the Smart can also be installed again on the primary side of the, sorry, wrong one, on the primary side of the plate heat exchanger and provide power and control monitoring. So on heating and cooling systems with zone measuring, again, we can use the same valve to provide our flow and power monitoring of each zone. Sorry, I'm looking at the wrong ones. So we've got 4 listed on these units itself. And then again, we can use those as isolation to shut those zones off when these parts of the building are not being worked on or worked in. And again, on the primary side of the plate heat exchanger to provide very accurate and high power control and monitoring. And then lastly, we can use from a data center point of view on crack units, we can do power control and monitoring on the crack unit itself. So just again, a brief touch on the TA Smart connectivity. So from bus, we have 4 bus protocols which are implemented on every TA Smart. So that means we don't have a version for BACnet or a version for Modbus or a version for IP over RS485. All of these options are available and wired into and configured into the Smart valve itself. So we have the serial on our RS485, which is our physical layer. So this is our 3-core cable, which is doing our Modbus RTU and BACnet MSTP. And then we have our Ethernet physical layer, so we can wire our Ethernet cable into the Smart box and do Modbus TCP or BACnet IP, which is ridiculously fast. And one of the 4 is to be chosen when at configuration time, when you're actually setting up and commissioning the valve itself. Analog, again, 0 to 10 or 2 to 10 VDC, and 0 to 20 or 4 to 20 milliamp can also be used. We can make that switch with a jumper, which is internal on the valve itself. So if we lift the lid, take the 4 screws out and lift the lid off the Smart control box itself, we're left with a jumper, and with the jumper in the position that we can see here, it's in 0 to 10 volts as an input signal. All we would need to do to change that to 4 to 20 is literally lift the jumper and place it across the two contacts, so we actually make the bridge and connect the circuit itself. And then, as I say, our output signal is 0 to 10 volt, 0 to 10 VDC only. The markings internally, as I say, there's the analog jumper, and this is the indication for it, which typically would sit here on the inside of the box. So these, what you can see on this diagram, would physically be printed onto the plastic of the smart box. This is probably one of the early development units that was used to photograph at the time. We then have the valve type, so our serial number, production date, what size the valve is. And then we have our LEDs. So these are our 3 power, wireless, and network LEDs. So these will indicate what the power is doing, if we're able to be wirelessly connected, or if the wireless connection is doing something, and if we're connected physically to a network itself. Then we have our RS485 termination resistor. So just in this section here, there's a little jumper. So we just need to change the jumper on the last unit. So if we're using a physical layer Modbus or BACnet, so RTU or MSTP, on the last unit of the run, we have to make this contact. So this resistance is included. So we have a 120 ohm resistance at the start, and this replicates 120 ohm resistance at the end. So it knows that this is the last valve in the sequence, or in the circuit, I should say. So our power supply, so this is our L24, this is our live 24 volt VDC, and our 0 voltage on the M. These are then next to the analog, so our input, which is our Y, and our XV, which is our output. Then the Ethernet, so within this section here, we can see the physical connections where we stamp the Ethernet cables into the unit itself. We don't have an Ethernet terminated switch, so there's no RJ45, if I'm correct, plug that's actually physically being connected into the valve. Typically, reels of cable don't come pre-terminated, so it makes no sense to have something like that on the unit, or externally on the box, which would also drop the IP rating, so we just don't do it. And then lastly, we have the RS485 connections. So this is our Modbus and BACnet over serial 485. This is where all 3 cables are wired into. We also have, what's not shown, unfortunately, this section here, there's another jumper which allows us to close the valve off wirelessly, so we can actually prevent wireless connection into the valve by changing the jumper and making the wireless connectivity within the valve dead. So if you've got certain sites where security is high and there's no wireless connections, we can ultimately switch once it's set up wirelessly, we can then turn the wireless off. And this is just the analog control smart wiring diagram. So as you can see, our 24 volts and 0 volts, and then our input and output signals. Then we've got our status LEDs. I won't go through all of these. These are just literally giving an idea of what's happening, what colours you should see, and what the meaning is for those colours. These are also included within the data sheet itself. And then our LEDs, which are the bottom row of 5 LEDs, which are indicating the current position of flow power. So one LED is between 1 and 20%. It's only for a physical rough idea of where the valve is from a position point of view. And these blink as same frequency as the TA slider. Calibration is the same as the motion, but with the LED fast blinking in yellow. So that will, if it's yellow and it's fast blinking, it means that the valve is actually calibrating, going through a calibration cycle presently. And then identification. So within the app itself, we can force what we call the green snake animation or night rider. So this is actually a run of blinking lights which runs from front to back, and you can physically see that on top of the valve. So if you've got multiple valves and you want to make sure you're working or setting up the correct one, you can run the indication process. So HyTune, instead of building a new app to use with the smart valve, we have just integrated the smart into HyTune. So now we can do smart valves and TA sliders on modulators and compact Ps. So very briefly, this is the interface screen that you see when you start the app. We can click the start scanning for devices. This opens up another screen and we see that the scanning is in process. And then once the scan's finished, it will show us the available units that are within the vicinity of the phone itself or the device. So we can then click that and take us through into the setup itself. So this is the main screen. Here we can see our live feed. So this is displaying our delta T, our current temperatures, flow and return, the fluid. So if it's water or if we've set it to be with glycol or and what percentage, we can see our flow, our input signal, and then the opening as well. And then this is our gauge. So this is showing the indication of where the percentage of where the valve is being controlled currently with regard to its assigned maximum value. Then our config frame. So this is where we actually do our setup. So this is how we tell it how we want to control and what our input signal is and our max minimum flows. And then the charts below. So you can see the blue line, which is in liters per hour. So this is showing our flow, and then the yellow line is showing our kilowatts. So this is showing a rough indication of the usage and being plotted. So if we click the config frame, we can then go into some of the background setup. So with application, we can see that we've got the valve on the supply and the sensor is on the return. We can click return and that will switch. So we can set it up in either way, depending on how you actually want to do it. If we click fluid, we can then change our fluid from water to monoethylene or monopropylene glycol. We can change the percentage that's in the system, and also the freezing point if need be. And to be honest, I think that's grayed out based on a calculation from what you've selected and the weight of ethylene or glycol that you actually put into the system. And then if we click control, we go into our control settings. So we say here we want to control by flow or by power, what the limitations are. So what's our max flow, what's our minimum flow if it's not 0, because we can also set a minimum flow on 0 volts instead of fully closed. And our analog output signal if you actually physically want the output signal. And then there's overrides, which we'll cover on another day because there's more for showing how things work. So in summary, we've covered all of our fundamentals and the elements, flow accuracy and applications and the connectivity, and then obviously with the HyTune and Smart app, just very briefly. Thank you for listening, and if you have any questions, by all means, please feel free to send them over.